So in the last video, we got the turn manager working, and now the player and the NPC will take turns moving. Currently our NPC is using the same movement as the player. So when we click on the NPC, or when it's the NPC's turn, they're basically doing manual movement. So in this video I want to convert the NPC from manual movement to automatic movement. And we're going to do that using an algorithm called A-star. A-star is a graph theory based algorithm similar to BFS that uses cost heuristics to essentially find the perfect path from one point to another, and it's pretty efficient. So we're going to start by creating a new script for the NPC called NPC move. And for starters, NPC move is going to look just like player move. In fact, let me just copy NPC move into here and then remove player move. So let's go to our script and just going to go to player move, and just like player move, NPC move is going to inherit from tactics move. In a start, it's going to call the init function, which, remember, for tactics move init essentially gets all the game tiles, computes the half height of the character, and then adds it to the turn manager. Now I'm going to copy the inside, but I'm going to make some changes for update. Check mouse doesn't exist because the NPC is not going to be allowing player selection. However, we do need the turn-based, basically shortcut, so if it's not the turn, update will exit. And if we're not moving, this is where we're going to perform selection of where to move. And then, of course, just like the player, we move in the same way. I am going to leave find selectable tiles in here. And the reason is, if you've ever played a tactics game, it still shows all the potential moves of the NPC, even though it's going to use A-star to actually move. It still want to show to the user, hey, these are the places it can move, this is where it's picked, and then it's going to move towards it. So we're going to need a couple extra functions. One called calculate path, which I'm actually going to do first. And another one called find nearest target. And there's a third thing coming later, but I'll get back to that. So calculating a path is essentially finding where it's going to move to. So tile, target tile equals get target tile of the target, which we haven't defined the target yet. So game object target. Find nearest target is going to fill that in for us. The next thing we want to do is a function called find path, which has not been written yet with the target tile. And I'm just going to comment that out. That is actually going to go in tactics move, and this is going to perform the A-star. So the last thing we need in here is find nearest target. And essentially, for this example, all targets of this NPC will be those with the player tag. So I am going to find all game objects that have the player tag using the find game objects with tag function. And I'm just going to look for the player tag. So that's going to create an array of all player objects. Now I'm going to make a relatively simple AI here. It's just going to look for the nearest player unit. If you wanted to make a more advanced AI, you can put that code in here instead, or you can have some way of switching between them where it can find the nearest damaged unit or the most powerful unit, or sometimes special units. For example, I've played scenarios where there's a unit that the player has to protect, and if that player dies, and the player loses the level. And so the NPCs would target that player specifically and would chase that player down. So whatever method you're going to use, we're going to use distance. So I'm going to have the nearest, and the nearest is going to be our eventual target. And then the distance, because we need to check all of these for distance. And I just want to set the distance to infinity so that everything after this is smaller, which you'll see why as soon as I do this for each loop. So for each game object in targets, that's our array, we calculate the distance using vector3 distance from the position of this unit to the position of the object in the target array. Now, I'm using distance. It would actually make more sense to not use distance, but to use the square of the distance. Vector3 distances, when doing distance with vector3, actually has a square root in it. And because we're only looking for relative values, we could actually use, I think it's called the square magnitude, and instead of the distance. And so we could use that instead. In fact, that would be more efficient speed-wise for the computer since it's less math. But I'm just going to keep it simple. Now, if this calculated distance d is less than the distance variable that we defined above, then this object is closer. And because the very first time it's set to infinity and this object is going to be less than infinity away, the very first object will become the nearest. And we update the distance and we set the nearest equal to this object. So this is just the quick and dirty algorithm for finding the closest something based on distance. You compare the distance of the nearest, the previous nearest, with this new distance. If it is closer, meaning the distance is smaller, the new one becomes the current object that we're looking for. When this for loop is done, we can just assign the nearest target and that function is completed. So this will fill in our target, which is where when we calculate path, we'll get the target tile. Now we need to define the find path, which is the A star function, and that is going to be in tactics move. We have everything in tactics move. Just kind of keeping it as a generalized class that has all the helper classes for us underneath. There are things we're doing that breaks OOP, especially the solid paradigm. But for now, we're just going to kind of stick it all in here just to keep ourselves organized. Make sure it's protected or public. Reason is that if it's private, you cannot use it in the parent. Sorry, in the derived class. So if it was private, we would not be able to call it here. So it has to either be protected or public to be accessible in the child. Now, the first thing that we need to do when finding the path is the same thing we did for BFS, which is compute the adjacency list for this object using its jump height and the target. Now, why do I want to pass the target? This is actually an adjustment we need to make to the adjacency lists function. Currently it's using this jump height, which is fine. It's the same jump height. And so we can leave, we can either pass it in as a parameter or not. I'm just going to pass it in. But I also want to pass in the target tile. And then I'm actually going to pass that target tile into the find neighbor function in the tile. Notice how it breaks it. It also breaks find selectable tiles, which is an easy fix. You just pass the jump tile and null because we're ignoring the target in find selectable tiles because there is no target. But it does break the find neighbors function. So let's go to that and add it in there. It is tile target. And the reason we're adding that in there is that A star is going to find a path directly to the tile that we're looking for. The problem is that we cannot walk on that tile because that tile has a unit on it. Therefore, we can't step on it. Because we can't step on it, technically that's not our target. It is, but it isn't, if that makes sense. What happens right now is that that target is selectable, or actually is not selectable because there's a unit standing on it. And remember, any tile with a unit on it is not walkable. So we're going to fake that a little bit for now by just passing in the target. And we're going to pass it into all the check tile functions. Again, it's going to break it. And in check tile, we pass in the target. And the only change that we have to make is in the raycast. Now this raycast is making sure that there's nothing on top of the tile. However, we want, oops, it's not item, it's tile. It's tile equals target. So we also want to include the target. Even though there's something sitting on the target, we still want to include the target because we want to know the best path to that target. When we get to actually calculating the path, we'll drop that off and then we'll actually find the tile closest to the target, i.e. the one sitting next to the target. So ignore anything that has an object on top of it, or I should say include anything because that doesn't have an object. Also include this target tile that we've now added in Tactics Move. So either way, we are going to be able to get to that target even though there's something sitting on top of it. So after we compute the adjacency list, just like the other BFS algorithm, we do have to get the current tile. What tile are we standing on? It's kind of important because that's our starting location. Now, the A-star algorithm uses two lists, whereas BFS uses a queue, A-star uses two lists, open list and closed list. Now, the open list could also be a priority queue, which is not the same thing as a queue. It's actually not implemented the same way because it's going to be searched for a cost value every time, and a priority queue can solve that problem quickly. Because I don't actually want to write a priority queue right now, and C# doesn't have a built-in priority queue, I'm just going to use a list and an inefficient algorithm for finding the lowest cost, which we'll get to in a second. So let me make my open and closed lists. Now the open list is any tile that has not been processed, and the closed list is every tile that has been processed. We're not done until the target tile is added to the closed list. When the target tile is added to the closed list, we have found the best path to the target tile. Now to start, first thing we do, we add the current tile to the open list because that's the first tile we're going to process. Now, again, we're not going to assign a parent to the current tile because we want our start tile to have null. This allows us to actually use the same pathing code, i.e. the stack, with a couple changes that we're going to have to implement for finding the path from the target back to the start node. By leaving the start null, we'll be able to quickly find out which one's the start node. Now the next thing we have to do is we have to make a couple changes to tile. Tile needs extra data for doing A star. So we have variables for doing BFS. For A star, we need F, which is the cost, G, which is a cost as well, and I'll explain these more in a minute, and H. H is heuristic cost. So G is the cost from the parent to the current tile. H is the cost from the current tile, from the process tile to the destination. And F is G plus H. And it's used for, again, finding a best case path in the minimal amount of time. Also in reset, we need to set F, G, and H equal to 0. Make sure those get reset back to 0. And that's all we need to do for tile. We can actually close tile now. And then when we go back to tactics move, when we set up the initial tile, G is already 0, which is good because the distance from the start tile to the current tile is 0 because this is the start tile. And then we calculate H, which is the distance from the current tile to the target tile. Again, I'm using distance. If you want to make this a little bit faster, you can use the square magnitude, because all these numbers are actually just relative numbers. They don't have to be exact. The next thing we do is just set the F to the H. Really, F is equal to H plus G. Our G is 0 because we didn't even set it. We're just taking the 0 that we set in the tile. Therefore, we know it's 0. We don't have to add it, but we could. And we will be doing that later on. Okay, the next step is we now need to loop to process the open list. Now, there is a potential problem, and this is something to deal with later on down the road, is what do you do if there is no path to the target tile? So that is something that we will eventually have to cover when we have multiple units, especially multiple enemies. What if there's an enemy already sitting on the closest tile and you can't stand on the same place as another unit? That adds a little bit more complexity that I don't really want to cover right now, but you might need to do some combination of BFS, or you might need to just find out another place. And essentially what you're supposed to do is you're supposed to find the closest open tile to that area. So there's probably a way around it by shifting what the target tile is, but I don't want to cover that right now. I just want you to be aware that that could be an issue. So in the case of this open list ever being zeroed out, meaning there's no items in it, we've actually not found a path. So if we hit 0 before we actually find the target, there's no path. If there's no path, you need to figure out how to either make a path or skip the turn or move somewhere else. So something to keep in mind. I'm not going to cover it in this series, but it is an important thing to keep in mind. Okay, so we need to grab the next tile to process. Now, the good news is that the very first time it doesn't matter because there's only one thing in there. In the future, there's going to be, could potentially be a lot of nodes in there, a lot of tiles in there. So we need to find the one with the lowest F cost. That's actually what drives A star towards our destination. The least amount of distance traveled from the start node and the least amount of distance to the, well, plus the distance. So the distance to the start node plus the distance to the end. Whoever has the smallest value of f is the one that we're going to process next, but it has the greatest potential of getting us to where we're going. And that's where the efficiency comes in. So I need to make a function to find lowest f cost. Again, if we had a priority queue, we wouldn't have to do this. Priority queue would just give us the value, but I'm not going to write a priority queue today. So protected tile find lowest f, and we're going to pass in the list of tiles called list. And really, we're just going to pass in the open list. But you could actually put it for any list. I'm just going to set the lowest to the very first tile to start with. And I'm going to make sure we return that tile. I know there's at least one thing in the list, because if there wasn't one thing in this list, the open list would be 0 and we would have exited out. So there's at least one thing in this list. So now I'm going to essentially loop through everything in the list. And just like our distance function, I'm looking for the lowest f cost. So if t.f is less than lowest.f, then this one, t, becomes the next lowest. Now, there's one more thing we have to do. We've now located the lowest. We know it has the lowest value of f. We have to remove it from the list. Once we find it, we remove it, because we're going to pull it off the open list and add it to the closed list. That means we're going to process this one next. So down here, we pass in the return value of lowest to tile t. It's already been removed from the open list. So the first thing that we do is add it to the closed list so that we never process this tile again. Meaning it's done. We've already found the best path to this tile here, this tile T. The second thing we do is that we check to see if this is the target. If we add the target tile to the closed list, we're done. We will have actually found our path. There's a couple things we're going to have to do, and I'm going to come back to that. So let me just put a to-do in here. We're going to come back to finishing that. I need a couple more functions to finish that. But for now, that is a stop case. And this is actually what we're looking for. This is our goal. We're looking for that target tile. When we hit that target tile, when it's in the closed list, we are done and walk away. And of course, we'll have our path at that point. That's one of the differences between this and BFS. The BFS algorithm, we weren't looking for a target. We were just looking for anything under the move. Here, we're looking for a target. When we find that target, we're done. Now, the next thing we have to do is we have to process the adjacency list for T. We're going to process all of the neighbors. Assuming it is not the target tile, we now have to continue moving forward by processing all of its nodes, anything it's connected to. Now, there are 3 cases when processing a node. Case 1, the tile is in the closed list. If the tile that we want to process is in the closed list, do nothing. It's already processed. So if it's on the closed list, we don't do anything to it. The second thing we do is look to see if it's on the open list. This is actually the hardest part of A star, and we're going to come back to this in a minute. But if it's on the open list, we have to check to see if there's a quicker way to get to that tile. But let me come back to that. Let me do the third case. And the third case is it's not on the open list. It's not on the closed list. Because it's not on the open list or the closed list, this is the first time we've seen this node. Since this is the first time we've seen this node, we add the parent. And the parent of this tile is T, because this is what we're saying. We're going from this tile, and we found a path to this child, or this neighbor. And then we calculate the costs. Well, there's G, which is the parent's G, plus the distance from this node to T, the parent. That gives us the G for the new tile. It's the G of the parent plus the distance to the parent. Next, we calculate H, our heuristic. Now, because we're doing a tile base, we could use what's called the Manhattan distance. But since we're using Unity and we're not using some kind of array, it's actually too hard to calculate the Manhattan distance here. So I'm just going to use just the basic Euclidean distance that we've been using all along. So vector 3 distance, tile transform position, which is the current tile that we're processing, to the target tile. So we have the G, we have the H. So the H is basically an estimated distance to the end. We have the G, which is the distance to the beginning. And F is just H plus G, or G plus H actually. It doesn't really matter. We're adding them together. Final step is we add this tile to the open list, meaning it's processed. And it'll eventually, potentially be processed in the future. So by sticking it on the open list, it can come through again. That goes back to the third case, or the second case. It's on the open list, but it's not closed. So that means we found a second way to a tile that's already been added onto the open list. It's possible that we found a faster way to this tile, meaning we found two paths to the same tile. So we have to check to see if the path through this tile is faster than the path from its previous parent. And we do that by comparing G-scores. So we create a temp G, which is exactly as if we're calculating the G for the first time. So we create a temp G, which this temp G is the same calculation for G right here. We're just saying, well, what if this tile's G is better? And that's what we're doing. If temp G is less than the tile's current G, if it's less, we found a faster way. So reassign the parent to T, and then update the costs. G is temp G. F hasn't changed, the distance, because the tile hasn't moved. So, H hasn't changed. So we add tile.g, which is the new G, plus H, the previous heuristic. H doesn't change from here because the target's not moving. All we've done is we've said we have found a new parent that gets us to this tile that we're processing right here. We found a faster way. And then we just update by comparing the G's. We know the distance is shorter. We are at the parent. We update the costs. Now, if the tile is equal, if the G's are equal or greater, then we didn't find a faster way and we do nothing. So that's just the 3 steps of A star. It's closed list, do nothing. Open list, see if we have a faster way of getting here by comparing the new G to the old G. If it is, this is the new parent. And then, obviously, if we've never processed this tile, we calculate, we assign the parent, we calculate its cost, and we add it to the open list. That's all there is to A star. It's just processing the open list by finding the lowest F cost, put in a close, checking for target, and then processing the adjacency and seeing if the tile is on the closed list, the open list, or neither, in which case it's added. And that's it for A star. It's a fairly simple algorithm once you kind of understand what's going on, which leads to what do we do when we find the target? Now, this goes back to one of our problems. We have found a path to the target. However, we cannot step on the target because there's a unit on that target. Now, in the future, you may want to be able to walk to a target that doesn't have a unit on it, in which case this code that I'm about to write isn't going to work. But in this case, I'm actually trying to walk up to a target and stand next to it. And so I don't want to stand on it, I want to stand next to it. And so I need to stop A star essentially one node in front of. And so I need to add a new function. Well, actually, I need to add a new variable first for A star purposes, and I'll make it public because I do need it later, called actual target tile. Actual target tile is going to be the target tile that we're actually going to move to in A star. And so let me write that in actual target tile. And so this is going to be the tile we move to. In order to find that tile, I need a new function, which we'll call, in fact, I need to make it protected just in case we want to use it later. Find end tile, tile T. So I'm passing in a tile, which is the tile, the target, and I'm going to look to see if I can find, oh, I know I can find it. I'm going to look to see what the tile is in front of it. So when we actually use it, it's going to be find end tile T. And then once we do find it, we can move to tile, just like we did in BFS, or actually just like we did with the player. But instead of moving to the end tile, instead of moving to T, we're going to move to the end tile, which is the tile in front of it. So we'll find the path to the target tile. But now we have to go and find the target tile, or the end tile, the tile that's going to be the one in front of the one we're looking for. So we're going to do a stack. There's also a secondary issue. And that other issue is A star will find a path across the entire map, but our unit can only move a certain distance, and it is possible that that distance is greater. Therefore, we have to only move part way. So that's the second reason we need to use the end tile, is not that we can stand, not just so we can stand in front on the tile next to the target, but so that we can calculate the path at the maximum distance we can move. So we're going to move towards the tile. Not, obviously, if it's out of range, we're going to still move to it along the path, but we're just going to stop short until our next turn. Of course, it's possible that target will move, in which case we'll have to end up recalculating anyway. So I need a new stack, because we're going to use similar code to actually finding a path, but we're going to make a slight adjustment. So just like finding a path and move to tile, we're going to get the next. However, instead of, and this goes back to what we were saying earlier, instead of actually assigning it to T, if you actually go to, if we go and look at the code for move to tile, it starts on the tile. We're not going to start on the tile. We're going to start on the parent. That's going to be the tile closest to our target, i.e. the tile next to our target. So we don't, again, we don't want to stand on him because there's somebody there. We want to stand next to him. And we calculate the path going all the way back. And we push And again, this is just like move to tile. We push it and we move on to the parent until we hit null, which is the start tile. So now we've created the path from the parent of our target, so the tile next to our target, all the way back to the start, which was the current tile. So now we have to do a couple of checks. The first check is the path count less than or equal move. Is it within range of this unit's move variable? And if the answer is yes, then actually all we need to do is return the parent, because that's going to be the target we're going to move towards. If it's within range, the parent becomes the tile we're moving towards. That's the easy case. The hard case is what if it's out of range? If it's out of range, we need to calculate what that tile is. And we're just going to do that by going from 0, less than equal move, I++. We know how many moves we can make. So we're going to step one at a time from the beginning, which is the start node, or the one next to the start node. And all we're going to do is pop end tile equals temp path pop. We just pop off each tile one at a time. And we only do it for the number of moves. And what ends up happening is that when we pop off the last one, whatever is left is the tile that we're going to move to. So essentially we start next to the parent, we grab that one, and we go up to move number of times. So we'll actually do it +1 because we started null. So we do it +1 and we pop until we reach move. And the one that's left, that's the actual end tile that we're going to move towards. So once we've done that, we're just going to move to that tile. This is just like the player. It's compiling for a second. Let me actually open up the player again. So in player, we want to find selectable tiles. And it's actually, sorry, it was over in check mouse. Once we found selectable tiles and then they clicked on the tile they wanted, we moved to that tile. So now the NPC is doing the same thing, except it's doing it in the A* in the find target function, the find path function. We're moving to the actual target tile, which is either A, the parent of the target tile, or it's the shortened path, meaning the up to the move of the parent. So we only have part of it. So we've now covered A*. We just want to do a couple more things, and the last thing we want to do is I just want to take the actual target tile and set it to true, set the target to true, which will turn it green, meaning we've actually found the target. Just like when the player clicks, now the NPC movement is going to click on the proper tile, and that's all that's doing, is it's going to turn it green. So now we should be able to see the NPC in action. So we hit play, and I believe the NPC had the first turn, and there he's moving part way. Now the player's turn. I'm going to move away from him. And he's moving, there he's down there. Let me move into the corner. He's still there, and now let me move partially, and he's going to actually find the tile next to the player. And he'll just chase the player around. And if I move on the other side of him, he actually won't move because he doesn't need to move. Now you notice that as he's moving, you can see his selection. I should probably put a delay in there. But you see his selection, his potential selection, even though he's using A*, still showing the BFS for potential moves. And he's just using A* now to chase the player around to get in position. Now, This is a melee character, meaning he's going to come up next to you and hit you. This is not a ranged character. If you were doing something with ranged combat, he wouldn't need to stand next to the target. That's just something you'd have to keep in track of when actually finding, what's the range of the weapon. And it's something you'd have to keep track of. Also, there's a potential problem here is, now while I don't have any blocked paths here, if I did, and one of the units ran out of turns, you wouldn't have any place to move because you can't move on to the target next to you. We could potentially have a problem, and we don't have a way around it. But again, this is just movement. Eventually, you're going to want to make changes so that the turn is based off of actions and not off the movement. So that finishes up the movement series. We've done player movement. We've done NPC movement. In fact, we just finished NPC movement using the A-star algorithm and having it go a partial distance, not the full distance, because again, only so many moves that the character can do. And so I hope you enjoyed this series on tactics movements. Thank you very much.